Let's talk about spin. The word itself makes you think of something. A spinning top, a basketball on a finger, a planet turning on its axis, and for a long time, that's what physicists thought too. When they first found this new property of particles, they called it spin, because it acted a lot like the angular momentum of a tiny spinning ball. It seemed like a good name, but it was wrong. Or at least, it was misleading. A particle like an electron is not a tiny solid ball. It's a point particle. As far as we can tell, it has no size, it has no surface, it has no parts to rub against each other. So, how can it be spinning? If you try to imagine a point with zero radius spinning, you run into problems fast. The surface would have to move faster than the speed of light to have any angular momentum at all. It just doesn't work. So, what is it? The honest answer is a bit of a letdown at first. Spin is an intrinsic, fundamental property of a particle, just like its mass or its electric charge. An electron has a charge of 1. It has a mass of about 9.11 times 10 raised to the power of 31 kilograms. And it has a spin of 1 too. You can't change these things. You can't make an electron stop having charge. You can't make it have more mass. And you can't make it stop having spin. It doesn't get spin from spinning. It just has spin. It is part of its definition, part of what makes an electron an electron. That's the simple, boring answer. But it's also the most accurate one. The name spin is a historical accident. It's a label we gave to a behavior we saw, and the label stuck because the math of that behavior looks almost identical to the math of a spinning object. It has angular momentum, it creates a magnetic field, it acts like a tiny spinning thing in so many ways that we just kept the name. It's a useful analogy as long as you remember that's all it is. An analogy, a convenient fiction. To really understand what spin is, we have to go back to when it was discovered. It wasn't predicted by a theorist in an armchair. It was forced on us by an experiment that gave an answer that made no sense at all. This happened in 1922. Two physicists, Otto Stern and Walter Gerlach, wanted to test a new idea in quantum mechanics. The idea was that certain properties in the quantum world might be quantized. This means they can only exist in specific discrete amounts. Think of it like a staircase instead of a ramp. On a ramp, you can be at any height you want. On a staircase, you can only be on step 1, or step 2, or step 3. There's no step 2.4. A lot of early quantum theory suggested that angular momentum in atoms worked this way. It was quantized. Stern and Gerlach decided to test this. They designed a clever experiment. They would take a beam of silver atoms and shoot them through a magnetic field. A silver atom is a good choice. It has 47 electrons, but 46 of them are arranged in a way that their magnetic effects cancel each other out. That leaves just one lone electron on the outside, so the whole silver atom acts like a single electron in terms of its magnetism. It's like a tiny flying magnet. The magnetic field they used was not uniform. It was specially designed to be stronger at one end than the other. Why? Because a magnet in a uniform field will just rotate to align itself. A compass needle does this. But a magnet in a non-uniform field will be pushed. If the north pole of the tiny magnet is in a stronger part of the field than its south pole, it will be pushed in that direction. If it's oriented the other way, it will be pushed the other way. So here's what they expected. The silver atoms would be coming out of an oven, all jumbled and hot. Their little internal magnets, their single outer electrons, would be pointing in random directions. Some would be pointing straight up, some straight down, some sideways, some at a 45-degree angle. Every possible orientation should be there. When this random spray of tiny magnets pass through their big magnet, they should be deflected. The ones pointing mostly up would be pushed up. The ones pointing mostly down would be pushed down. The ones pointing sideways wouldn't be pushed up or down at all. They just go straight through. The ones at an angle would be pushed up or down a little bit, so what should they see on the detector screen at the end of the experiment? They expected a smear, a continuous vertical line. The atoms would land all over the place, from a maximum up position to a maximum down position, with every spot in between filled. This was the classical common sense prediction. They ran the experiment. It was difficult. They were using a weak beam of atoms and looking for a tiny effect. The story goes that they couldn't see anything on their detector plate at first. Stern was so disappointed he left, but Gerlach stayed and looked closer, holding the detector plate near a lamp. He was smoking a cheap sulfurous cigar, and the cigar smoke reacted with the faint silver deposits on the plate, making them visible. And what he saw was not a smear. It was not a continuous line. It was two dots. Just two. two distinct separate spots. It was as if every single silver atom, when it entered the magnetic field, was forced to make a choice. It could either be deflected all the way up or all the way down. There was no in between. There was no halfway. There was no going straight through. This was bizarre. It was impossible according to the physics of the time. It was like flipping a million coins and having every single one of them land perfectly on its edge in one of two opposite positions. The atoms weren't oriented randomly. They were only ever found in one of two possible states. Up or down. This property, this two-valued ness, was a mystery. They had discovered quantization of angular momentum, but in a way no one expected. It was a new kind of angular momentum. It wasn't from the electron orbiting the nucleus. That was already understood. This was something else, something intrinsic to the electron itself. A few years later, two other physicists, Goudsmit and Uhlenbeck, proposed the idea. What if the electron itself was spinning? A spinning charge would create a magnetic field, just like a tiny bar magnet. And if it could only spin in one of two ways, clockwise or counterclockwise, that would explain the two dots. They called it spin. But, as we said, the idea of a tiny spinning ball didn't really work. The math, however, was perfect. The mathematical description of a quantum property that could only have two values perfectly matched the experimental results. So the name stuck even if the physical picture was flawed, so spin is quantized. For an electron, it can only be up or down when you measure it along a certain direction. We call these values plun, 2, and 1, 2. Don't worry about the fraction for now, just think of it as a label for the two states, up and down. But here's where it gets even stranger. Before you measure it, the electron isn't in an up state or a down state. It's in a quantum superposition of both. It's a mix of up and down at the same time. It only chooses one when you force it to, like by sending it through a magnetic field. Let's say you send a beam of atoms through a Stern-Gerlach device that is oriented vertically. The beam splits into two, an up beam and a down beam. Now you block the down beam and take only the up beam. Now you have a pure beam. Every single atom in this beam is in the spin up state. You know this because you just measured it. What happens if you send this pure spin-up beam through another identical, vertically oriented magnet? You'd expect them all to go up again, right? And they do. The beam goes up, no surprises there. But what if you take your pure spin-up beam and send it through a second device that's oriented horizontally instead of vertically? It's now measuring spin along the left-right axis. What do you see? Common sense would say that if the spin is up, it has zero component in the left-right direction. So the beam should just go straight through, undeflected, but that's not what happens. The beam splits again. It splits into two beams, a spin-left beam and a spin-right beam. Exactly 50% of the atoms go left and 50% go right. This is fundamentally weird. The act of measuring the spin in the horizontal direction completely erased the information about its vertical spin. The atoms that were definitively up are now definitively left, or right, and have no memory of ever being up. Let's take it one step further. You take that spin-right beam that just came out of the horizontal device, and you send it back through a third device, one that's oriented vertically again. What happens now? You might think that since they all started a spin-up, they should all go up again. But no, the beam splits again. 50% go up, and 50% go down. The information is completely lost. Measuring the spin along one axis randomizes it along the other perpendicular axes. This is a core feature of quantum mechanics, related to the uncertainty principle. You can know the spin perfectly along one direction, but then you know nothing about its spin along the other two directions. This brings us to the weird number 1, 2. Why is an electron a spin 1, 2 particle? This number tells us something profoundly strange about the nature of spin. It relates to how the particle behaves when you rotate it. If you take a normal object, like a chair, and rotate it by 360 degrees, it comes back to looking exactly the same. That seems obvious. A full rotation brings you back to the start. The same is true for a spin 1 particle, like a photon, a particle of light. If you rotate it by 360 degrees, its quantum state returns to what it was. An electron is different. If you take an electron and rotate it by 360 degrees, its quantum state does not return to what it was. It becomes the negative of its original state. The math that describes the electron state, called its wave function, gets a minus sign in front of it. This doesn't change most measurable things like where it is, but it is a real fundamental change in its mathematical description. To get an electron back to its original state, you have to rotate it a full 720 degrees. 2 full rotations. This is almost impossible to visualize. How can something need 2 full turns to get back to where it started? There's a famous analogy that helps. It's sometimes called the plot trick or the belt trick. Imagine holding a dinner plate flat on your hand, palm up. Now, try to rotate the plate 360 degrees without twisting your arm into a knot. If you rotate it over your arm gets twisted. If you rotate it under your arm gets twisted. Your hand is now in a weird, strained position. It is not back to its original state, even though the plate is. But now, keep going. Rotate the plate another 360 degrees in the same direction. As you complete the second turn, you'll find your arm can unwind itself and return to its original, relaxed position. Your hand and the plate have both returned to the start after 720 degrees of rotation, not 360. Your connection to the plate is like the spin 1-2 particles connection to the wider universe. It has a kind of topological relationship that is more complex than it first appears. This 720-degree symmetry is one of the deepest and strangest features of spin. It's not just a mathematical curiosity. It's a fundamental property of the universe that particles like electrons, protons, and neutrons all share. This property, this spin number, turns out to be one of the most important things about a particle. It divides the entire universe of known particles into 2 great families. The first family is called the fermions. These are all the particles that have half-integer spin 1, 2, 3, 2, 5, 2, and so on. This family includes all the particles that make up matter. Electrons, protons, neutrons, quarks. They are the bricks of the universe. The second family is called the bosons. These are all the particles that have integer spin 0, 1, 2, and so on. This family includes the particles that carry forces. The photon, which carries the electromagnetic force, is a spin 1 boson. The gluon, which carries the strong nuclear force, is also spin 1. The Higgs boson is a spin 0 boson. They are the mortar of the universe. Why is this division so important? Because fermions and bosons behave in completely opposite ways when you get a bunch of them together. It all comes down to a rule called the Pauli exclusion principle. The Pauli exclusion principle, which is a direct consequence of spin, states that no 2 identical fermions can occupy the same quantum state at the same time. What does that mean? Think of quantum states as seats in a theater. The exclusion principle says that for fermions, there can only be 1 person per seat. If an electron is in a particular state defined by its energy, its location, its spin, etc., no other electron in the same system can be in that exact same state. They are fundamentally antisocial. This one rule is arguably the reason we exist. It's the reason matter is stable and takes up space. In an atom, electrons fill up energy levels, or orbitals, around the nucleus. The first orbital can hold 2 electrons, one with spin up and one with spin down. Once those 2 seats are taken, the next electron has to go into a higher energy level. It's excluded from the lower level. This forced stacking is what gives atoms their structure. It's what creates the periodic table of the elements. It's what underlies all of chemistry. Without the exclusion principle, all the electrons in an atom would just collapse into the lowest possible energy state, and atoms as we know them, with their rich chemical properties, wouldn't exist. Matter would be a strange, dense soup. The fact that you can't push your hand through a table is at a very deep level because of the spin 1-2 nature of the electrons in your hand and the table, which refuse to be in the same place at the same time. Bosons are completely different. They have no such rule. In fact, they love to be in the same state. They are fundamentally social. You can pile as many identical bosons into the same quantum state as you want. There's no limit. This property is what makes lasers possible. A laser is just a huge number of photons all in the exact same quantum state. They have the same frequency, the same direction, the same phase. They act as one single coherent wave of light. You can't make a laser out of electrons because the exclusion principle would forbid them from getting into that single state. This clumping behavior of bosons also leads to other strange phenomena like superfluids, which are liquids that can flow without any friction, and Bose-Einstein condensates, a state of matter where millions of atoms cool down so much that they all fall into the single lowest energy state and start acting like one giant superatom. So spin isn't just a weird little property, it's the organizing principle for the entire universe. It separates matter fermions from forces bosons. It dictates the structure of atoms, the rules of chemistry, and the stability of the world around us. And it has practical applications we use every day. The most famous is probably magnetic resonance imaging, or MRI. When you go into an MRI machine at a hospital, you are being placed in a very strong magnetic field. Your body is full of water, and water molecules contain hydrogen atoms. The nucleus of a hydrogen atom is just a single proton, and protons, like electrons, are spin 1-2 particles. The strong magnetic field in the MRI machine makes all these tiny proton magnets line up, mostly in the spin-up direction. Then, the machine sends in a pulse of radio waves. This radio wave is tuned to exactly the right frequency to be absorbed by the protons and make them flip into the spin-down state. When the radio pulse stops, the protons relax and flip back to spin up. And in doing so, they release a little bit of energy, which is detected by the machine. Potentially magnetic fields and radio waves, and by measuring the signals coming from different parts of the body, a computer can build up a detailed 3D image of your internal tissues. The water content of different tissues like fat, muscle, and bone is different, so they produce different signals. And MRI is literally an image of the quantum spin of the protons inside your body. Another huge area is magnetism itself. Everyday magnets work because of electron spin. In most materials, the electron spins are oriented randomly, so their little magnetic fields all point in different directions and cancel each other out. The material isn't magnetic, but in certain materials like iron, the electrons can influence their neighbors. Under the right conditions, they can all align, with their spins all pointing in the same direction. When that happens, all their tiny magnetic fields add up to create one large, strong magnetic field that you can feel. A permanent magnet is just a piece of metal where trillions of electron spins have decided to point in the same direction. Even in modern technology, spin is at the forefront. The field of spintronics tries to use the spin of electrons, not just their charge, to store and process information. This could lead to computers that are much faster and use less energy. And in the world of quantum computing, the up and down states of a particle spin are often used as the 0 and 1 of a quantum bit or qubit. The ability of spin to be in a superposition of both up and down at the same time is what gives quantum computers their potential power. So, let's circle back to the original question. What is spin really? We've seen that it's not a tiny spinning ball. We've seen that it's an intrinsic, unchangeable property. We've seen that it's quantized, only ever appearing as up or down when measured. We've seen its weird 720-degree symmetry. We've seen how its value divides the universe into matter and forces, gives structure to atoms, and makes the world solid. The deepest answer from modern physics is that spin is a consequence of the relationship between quantum mechanics and special relativity. When you combine these two great theories, you find that particles must have this property. It emerges from the fundamental symmetries of space-time. It's a required label that every particle must carry, a bit like a name tag, that describes how it behaves when you rotate it or move it around. The math tells us that this property must exist, and that it must have the mathematical form of angular momentum. So we call it spin. We call it that because the mathematics of this fundamental property is the same as the mathematics of angular momentum. It's a name born of analogy. Perhaps the best way to think about it is this. Don't try too hard to visualize it. Our brains evolved in a world of big, slow, classical objects. We are good at picturing spinning tops and planets. We are not equipped to picture a property of a point particle that needs 2 full rotations to return to its starting point. Our language and our mental pictures fail us at this level, and that's okay. Physics isn't about finding comfortable analogies for everything. It's about finding a mathematical description that accurately predicts the results of experiments. And the theory of quantum spin is one of the most successful theories ever developed. It has been tested in countless ways and has never been found to be wrong. So spin is real. It's as real as mass and charge. It is a fundamental number written into the fabric of a particle. It's a label that tells the universe whether that particle is a loner or a social butterfly. It tells matter how to build itself into stars and planets and people. It is a quiet, hidden property that you can't see or feel directly, but which, in many ways, is responsible for the entire structure of the world we live in. It's not a spinning top, it's something much stranger and much more important.